Hi, everyone. So now I will conclude some of the discussions of the octahedral crystal field, and then we'll get into how to calculate ligand field stabilization energies later. But recall where we were. We've already established that the ligand field splitting or the crystal field splitting del O in the octahedral crystal field, which is described right here, actually dictates not only the magnetic properties of the compound, it will actually give rise to the D to D transitions. And just for the sake of argument, if the ligand field splitting here was 20,300 wave numbers, and you took an absorption spectrum, this is approximately what you would actually see, and you see that transition that's centered at that energy that's right there. And of course, the way to visualize this is wavelength is always in nanometers. So what you want to be able to do is to convert wave numbers into nanometers, you basically just need to use that simple equation. So you basically take the inverse of the value in wave numbers and multiply it times 10 to the 7th, and that'll convert it directly into nanometers. So in this particular case, for that absorption profile, the peak of that absorption is at 493 nanometers, and that is effectively in the blue-green region of the electromagnetic spectrum. So it's like right in the middle of the visible spectrum, and this is why transition metals, they're D to D transitions that are actually forbidden, but they're slightly allowed, as you'll find out in chapter 11. But what happens ultimately is that the color that you see in the transition metal complex is going to be proportional to the del O value. And that's something that's going to be really interesting as we move on. So not only magnetic properties, but also the color properties. And then we've also talked about how oxidation number in the metal center influences the energies of del O. And then we talked a little bit about the nature of the ligands. So let's kind of continue that discussion. So as I said, the spectrochemical series, which is really just illustrating the fact that the ligand field strength is going to dictate the color because it dictates the magnitude of del O to a certain extent, and that is what we really, want to focus on. But right now, the reason why you see these trends are not going to be obvious, because once we talk about ligand field theory, it will become much clearer. But you really have to understand that it's going to be the sigma and or the pi donor and acceptor properties of the ligands that are going to dictate where it falls in terms of ligand field strength. And the way to think about this is the strong field ligands are over here. The very weakest field ligands are over here, and then intermediate, they're also kind of relatively weak. You see that there's no necessary correlation of any of this to basicity or any other sort of concept that's familiar from organic chemistry. So we're going to have to deal with this, as we talk about the electronic structure of the ligands themselves. But the clear indication here is that strong field ligands give you large del O separations, and then weak field ligands give you small del O separations. So you can see that's the strong field ligand and weak field ligand. And the other thing to remember is strong field also implies you make stronger bonds. Weak field also implies you're making weaker bonds. It's another way to think about it. So of course, all of this is then proportional to formation constants. But let's not worry about that at this moment. So the next topic, which I think is really important to cover here, is you can actually deduce by simply the same electrostatic repulsion argument, you can actually then figure out what are going to be the d-orbital energies in a variety of different molecular geometries. So octahedral, for example, we have a D9 system here. So this is synonymous with, say, copper 2. So it's D9, And what you basically get from this is if you recall where we are here, these are the T2G and these are the EG orbitals. And then what are we doing? Well, if you kind of go from octahedral to this tetragonal distortion, which is the D4H point group, remember, this is now like, you know, descending symmetry or descent in symmetry. And you can actually do this exactly off the character tables, but I don't want to take a group theory approach here. I just want to do the electrostatic appearance. So octahedral environment, remember X, Y, and Z ligands are all effectively equivalent. So they're all repulsing to the same extent. That's why X squared minus Y squared and DZ squared are actually degenerate. They're both, you know, up here. You start to do a tetragonal distortion. What did you do? Well, the Z ligands are basically stretched out of the same bond distances with respect to the other four ligands. So basically, a simple way to do that is to basically pull the Z ligands out. Is another way that I like to kind of write this out. So what does that mean in terms of electrostatic repulsion? Well, let's work on the EG orbitals first. So if you pull out the ligands on the Z-axis, you're going to stabilize dz squared, and that's exactly what happens. So dz squared is stabilized when you do a tetragonal distortion. But then what else happens? Well, if you stabilize dz squared, you also stabilize any of the orbitals that are, you know, sort of in the Z plane as well, because you're removing electron repulsion in that direction. So you also stabilize dxz and dyz. See, the Z components are contained in both of those. And then what does that then do? Well, if you removed the stress effectively on the Z-axis, then you have an increased stress on the X and Y axes. So correspondingly, you destabilize dxy. And then, of course, you also are going to destabilize dx squared minus y squared. So you see what happens. The tetragonal distortion takes degenerate orbitals and it basically removes the degeneracy. That's what happened. So you see now all the orbitals of highest energy are now no longer degenerate, and it's because we lowered the symmetry. So molecules tend to do this, they'll lower symmetry. Okay, well then what else can we do? Well, then we can go really extreme. Let's pull out Z completely. So let's now remove the Z-axis ligands completely. What's going to happen with respect to tetragonal? Well, then we're going to square planar. And square planar, remember, is still going to be the D4H point group. We're just removing the axial ligands. But if you do that, Z squared stabilizes even more, because you've totally now removed the ligands completely. It has very little influence on XZ and YZ with respect to the stretched situation. So those just kind of walk their way over. And then, of course, if you completely remove those, you then also have an influence on the fact that XY will be slightly higher in energy than Z squared. And then X squared minus Y squared, you know, it's kind of about the same. But you see what now happens. Now you have the energetic ordering of what happens in a square planar environment with respect to the tetragonally distorted and the octahedral environment. So all we're doing is we're just assuming electrostatic repulsion on Z is the only thing we're manipulating, and you get to all of these electron configurations. And then you can kind of now see why square planar molecules, a D8 configuration, is actually particularly stable, because you're not actually putting anything in the last d orbital, but you're filling the rest. Okay, well, what other geometries do we really have to worry about in terms of crystal field theory? Well, we run into a lot of tetrahedral molecules as well. This is now interesting because in the tetrahedral field, now we're going to use the tetrahedral point group and the tetrahedral character table. And now what happens in those particular cases is the G's and the U's are now removed from contention with respect to the octahedral point group. So you'll see what happens is instead of T2G, we have now T2, and instead of EG, we now have E. So that's how they're going to correlate when you do reduction in symmetry again. But it doesn't really matter. What we care about now in the tetrahedral geometry is, if you recall, the displacement of the ligands now is effectively like it is on the hydrogens and methane. So what you really have is you have like one ligand. Let me draw it somewhere else here. You have one ligand that's pointing up, and then you're going to have like three other ligands that are basically in a triangle and a base. And the triangle you can kind of draw any way you like, but basically you have one of them pointing out towards you and one of them going back. But it gives you the idea that you have this triangle and then or like a tripodal sort of arrangement. But what that really does is it inverts the electrostatic repulsion. So now what happens is the T2 orbitals that were in the octahedral field in between the bonding axes, now they're coinciding with them. So that basically means that dxy, dxz, and dyz are all now in the T2 configuration, same as they were in the octahedral environment, except now with respect to the spherical field, those are now destabilized. And then as a net result of that happening, what happens to the E set? Well, those are now, the net result of that is those become stabilized. So the tetrahedral field is basically the inverse of the octahedral field in terms of where the d orbitals go. And then the same thing we did before, remembering that right here is the barycenter or the center of gravity. You have to conserve energy. So if three orbitals are up here now and two are down here, then you basically have the same situation we had with octahedral, except now we call it delta T or del T for tetrahedral. And what happens is if the three orbitals are up here, then above that center of gravity, it's going to be 2/5 delta T or del T. And then obviously if three orbitals are up top, two are at the bottom. So that means that 3/5 del T go down. So you can actually calculate a tetrahedral field splitting energy, much like you could with octahedral, except that the situation is just reversed in terms of the energetic ordering. You still got a doubly degenerate set here and a triply degenerate set here. They're just, of course, the doubly degenerate set is stabilized. The triply degenerate set is destabilized. So let's look at this on a bigger picture. So what you get in all of the commonly observed geometries is really shown here. So remember, if you just have the free ion here, those energies are basically without having any ligand point charges around it. These go up in energy, remember, when you put a spherical ligand field. So this is the spherical ligand field, and that brings the energy up. And then if you put them in the tetrahedral complex, I want you to see something. That's now going to be del T. But look at the magnitude of del T compared to the magnitude of del O. And as a rule of thumb, for a given complex that has the same ligands but is in a tetrahedral versus octahedral environment, del T is about 4/9 the magnitude of what del O is. That's kind of the typical rule of thumb, and that's what you see here. This magnitude here tried to focus it down too much here, but the magnitude of that splitting is about, you know, a little less than half of what it is for the octahedral case. It shows you the ordering of all of these orbitals. And then the other thing that really comes about here is if you kind of compare tetrahedral to octahedral and then go over to square planar, remember this here is just going to be a reduction in symmetry. And the reduction in symmetry is effectively telling you I'm just removing the z-axis components, and by removing the z-axis stress, look what happens. All of the z component orbitals are stabilized, and the xy component orbitals are destabilized. So that really summarizes all of the energetic pictures that you're going to see in terms of the d-orbital splittings in a lot of these common geometries. And I hope that was clear. And when I come back next time, we will talk about how you calculate the Huygens field stabilization energies under all of these different circumstances. And thank you.